It's hard to argue when you're never the same side. You found the lies I built around me, made up some brand new ones about me. Baby, I love the way you're looking in this good light. I love you cause I don't love me. I love you cause I don't love me. I love you cause I don't love me. I don't think I deserve better. This is not even about you. I lost me before I found you. I love you cause I don't love me. I don't think I deserve better, but we deserve better. Sometimes I see a piece of what this could be. I'm terrified to let you go. But if you give me half your heart, I'll never have your heart. Two half hearts don't make a whole. I just want someone to love me. Come on, somebody just love me. I love you cause I don't love me. I love you cause I don't love me. So I don't love you, I don't love me. I don't think I deserve. This is not even about you. I'm alone with or without you. I love you cause I don't love me. I don't think I deserve better, but we deserve better. We deserve better. I know you know the power in your text, perfectly timed at 1 a.m. Suddenly there's tension in my chest, feels like I'm running when I'm standing still. You're controlling every part of me with 6 words. The crazy part is that I tell myself it don't hurt, but the truth is I love you cause I don't love me. I love you cause I don't love me. I love you cause I don't love me. I don't think I deserve better. I can't feel it when you touch me. We're not fooling anybody. I love you cause I don't love me. I don't think I deserve better, but we deserve better, better. You cut me down so we never see eye to eye. It's hard to argue when you're never the same side. You found the lies I built around me, made up some brand new ones about me. Baby, I love the way you're looking in this good light. I love you cause I don't love me. I love you cause I don't love me. I love you cause I don't love me. I don't think I deserve better. This is not even about you. I lost me before I found you. I love you cause I don't love me. I don't think I deserve better, but we deserve better. Sometimes I see a piece of what this could be. I'm terrified to let you go. But if you give me half your heart, I'll never have your heart. Two half hearts don't make a whole. I just want someone to love me. Come on, somebody just love me. what we deserve.
So I took this doubling every year and extrapolated it 10 years from 1965 to 1975, from 60 components to 60,000 components on a chip.
First thing you have to tell him is, guys, we've been giving you a free ride for 30 years while you write your crummy software and we made it faster. Right? That's over.
The future is parallel. Single cores are not getting any faster.
All right, welcome to CSE142 again. And today we are continuing our discussion on performance. In the last lecture, we talked about what is performance. And today I'm going to tell you how we can get better in terms of performance. And last lecture, we learned that the very classic performance equation is determined on the execution time of your program running using a processor. So the performance is defined by 1 over execution time, because longer the execution time, the worse the performance. So the execution time, as you could easily imagine, because of the von Neumann architecture, your programs are compiled into instructions. So instructions per program, or say instruction count, which we abbreviate it as IC, should be one of the factors. And each instruction takes a certain amount of time to execute. And that certain amount of time is determined by how many cycles it takes to execute an instruction and how much time it needs for a cycle. So it turns out, and the cycle time is also the inverse of the frequency. So that's how we got the execution time. And you can memorize this ET equal to IC times CPI times CT. And however, as a computer scientist, most of the time you probably won't count this execution time directly like we can do in a class. However, it's really important for you to understand what makes the performance difference and figure out how can I improve the performance of my code. So for the left-hand side and the right-hand side, they both have the same algorithm complexity. They have similar instruction count. It's the same processor, so the clock rate is the same. But however, as you remember, the last time we ran the code, the left-hand side is probably significantly faster than the right-hand side. So, and the main reason is because it has better CPI, and who can make the difference is actually the programmer. So the programmer can change the CPI. And last lecture, I have a demo, but I failed to run it, and I figured out why. And it's just because of the permission was not setting right. So I rewrite. I'm here to show you the demo. So now I have I changed my program a little bit, so you will feel it's more the programmer's change. So now I modified the matrix addition code a little bit in a way that I take another argument, and if I have that argument, then I would adjust my CPU frequency to be just 1.2 gigahertz maximum. So here, this command is actually saying that, can you override this value to be the scaling maximum frequency of each processor? And the machine that I'm testing right now, it will have 24 processors, and and it still do the same matrix addition code. And at the end, it will restore the frequency back to the processor's base code, the maximum frequency, which is 6.7 gigahertz. So this is the processor that I will be using today. It's an Intel 12th generation processor. And as you can see, it has 24 cores, and the baseline CPU are right now all sitting at 800 megahertz. And let me do one more thing. So let me run this. So now I create another instance to log into the machine. And if you do this, if you cat /proc CPU info, as what I just showed you, it will tell you a lot of things about your processor. For example, how big the cache size is, what's the model, and how many cores do we have. And if we do a little bit more, for example, if I can grab the megahertz one, it will list all the frequency of the processor's cores right now. And if you are familiar with the Intel 12th generation, it's actually a processor with big little cores, or say what they say, efficient cores and performance cores. So that's why you see some of them are in 600 megahertz, because those are the performance core with wider range of adjustable frequency, and 8 of them will be these are the efficient core. They range from 800 megahertz to 3 something gigahertz, as far as I remember. So that's the frequency that we have. So now let me run the program. Okay, so the program that I just showed you, right? So I wanted to run longer, so that's why I have a 32K by 32K matrices. And if I have an additional argument, it means that I'm right now slowing down the frequency. So, oops, sorry, I have to run this in root. Okay, so let me. So now, well, sorry, this is the version. Is it working? Wait. Okay, so right now, if I am running this program, okay, so this is the version that, oh, okay, because I don't pass the third argument. So right now, if you see this, right, the frequency, when I'm running these pieces of a code, they jump up to at most 5 gigahertz of processor cores when I am executing these pieces of a code. And the processor has some kind of dynamic mechanism that dynamically adjusts the frequency. So right now, if you just look at the frequency, it's going back to 600 and 800 megahertz. So now, if I'm adding another argument, which means that I am going to slow down the frequency, then let's see, right? And as I mentioned, and as we mentioned, right, we set the maximum frequency to be somewhere like 1.2 gigahertz. So when I'm running these pieces of a code, none of them can surpass the 1.2 gigahertz, or say 1200 megahertz, right? So comparing against the frequency that we were running the code without passing the third argument, it's a lot slower. And with respect to that, we can imagine the execution time would be a lot longer. So the previous version that we don't control the clock frequency, it only requires 13 seconds. But right now, it requires a lot longer than that. Like right now, I'm thinking about what to say, but it still hasn't finished yet, right? So you can imagine, wow, with this frequency adjustment, then the pieces of a code take surprisingly long time to execute. And surprisingly, it has been quite a while, but it hasn't finished yet. So yeah, and I have no idea how long it takes to finish. I thought it's something around like, okay, 1 minute and 12 seconds, right? And so right now, if you look at the frequency, everyone is back to the default base frequency. So this gives you an idea that the programmer can indeed change the frequency, can indeed change the cycle time. So if I ask you the question, like what programmers can change, actually everything. So that's why you guys are so important in performance. So we said that this is a peer instruction class, but to give you some incentives in team discussion, we divide you guys into 4 different teams. And the reason why it seems like yellow group has the most amount of people, but that's actually not right, because this is the way how I make the distribution evenly, and most of it, and yellow and I believe the rocket team should have the same amount of people. So that's kind of odd, because the PID distribution is not even. But so far, it seems like the yellow team is doing really well. But it's just the beginning of the class. So all of you still have like 17 lectures to go to get a chance of winning the Amazon gift card. But as our I want before every lecture, I really want you guys to have some warm up for discussion. So today, here's the warm up conversation that I want you to have within your group. What change will you make to improve your life, and why is that? Now you have 3 minutes to discuss that within your group. What is that? What is that? What is that? Wait a moment. Wait a moment. Where is that? Okay, here we go. All right, it seems everyone is back. So anyone would like to share your thoughts about what's the change you want to make in your life? Or if you hear some people saying about that, feel free to shout it out and tell us, why do you think that's something worth doing? Summon.
Yeah, can I go for sharing?
Sure.
So I think one thing that all of us need to change to improve our life, I think it would be change our habits, even for studying, because if we do more studying and we do extra coding, so we would be ready for some interview to get job.
Okay, so
I mean,
then when you make this decision, right? what are you trying to optimize for?
I think different thing. Maybe just do some optimization to get better results.
Okay, some optimization to get better result. Okay, cool. Thank you for sharing. Devi, what do you think?
Oh yeah, we're talking about a lot. It's like we should wake up earlier and then try to get stuff
Uh-huh.
done more in the morning instead of at the night.
And why is that?
Because I guess that like I guess getting stuff done at night kind of like encourages procrastination because like it's always a good mindset to like start early, start often, as they say. So I guess starting in the morning is a good starting point. I suppose.
Okay, so start in the morning would give you better, clear mind of working on things and potentially getting things done better or sooner, right?
Yes, yes.
Okay, thank you. Ewan, any question? Well, any idea?
We said we could do some sports every day to make our brain more excited and we can get a better attitude towards work. Yeah.
Okay, so exercise, get better attitude for work outcome, right? Okay.
Yeah.
Kayat?
Yeah, we couldn't get to everybody in our group, but one of us said probably the exercising thing. But what I said was probably get a specific schedule throughout, like for the rest of my day. So I'm doing specific things at specific times. So when there's a set time frame, you are in the mindset of work for that stipulated time, right? Like for example, when we were in middle school or preschool, our school time would be from 9 a.m. to 1 p.m. or something like that. And after that, we would not think about school at all. But during that time, we don't do anything else. We just work.
Okay.
That's all.
Very focused.
Yeah.
Right.
More focus. Yeah.
Okay, so from here, right? Everybody is trying to optimize for the outcome of their study or maybe the outcome of future employment, right? And or the efficiency in general, right? So based on that, I think when you have that answer, there must be something that you pop up in mind. Okay, this is my shortcoming. Maybe the reason why I thought about exercising is because the reason why I'm not very efficient is because I don't have very positive attitude, or sometimes you think about I need to make my schedule is because sometimes I really want to focus, but it's just not the time that I get used to be focused. So I really want to develop that kind of hobby or that kind of habit, right? So that's why you guys have that conclusion. So today, what we are going to continue our discussion on a performance equation, and in addition to that, we are going to talk about one law in computer architecture called MDOS law, and you will figure out that MDOS law is not just a scientific law. It could be applicable to all aspects of your life as well, which you might find that when you were talking about the answers that you just shared with us, there may be some flavor of MDOS law as well. So last lecture, we ended at a question, how programming languages affect performance. And then I checked that most groups end up with the answer of 2. So, but because of the short of time, we don't have too much time to talk about this. So now I'm inviting one of the group. If some of you remember what was your discussion in the last lecture, feel free to share that. So raise your hand, shout it out. Like, what do you guys have in mind for a group discussion? Okay, Michael.
Yeah, I think depending on like kind of how high or low level the programming language is, you'll have to go through certain abstractions that will affect the amount of instructions for each operation and also the difficulty of that operation, how many like system calls you'll have to make for it, and etc.
So then instructions count, and what's the other thing that it would affect?
The cycles per instruction, because like
Cycles per instruction, right? Okay.
mhm.
So Michael, I believe you are in the rocket team. Okay. So right now, thanks for sharing, right? So I think most of you agree that programming language affect both the instruction count and the CPI. And now it affects the instruction count. So I will start with this question. What's your favorite programming language? Your favorite programming language, this one. All right, it seems like 90% of you have sent in an answer. So let's wrap up in 10 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so let's look into the answer, and looks like oh wow, so we have a big group of people embrace the idea of C++, which is surprising to me. And also the same amount of you think, well, I love Python, right? And Java second both. And then least amount of you think I like Perl or C. Okay, so that's what you have learned. So now the second question that I'm going to ask, regarding these 5 programming languages that we just sing, if I just want to implement a program that prints hello world on screen, which of the following needs the highest instruction count? Wait a moment. Programming language. Oops. Programming languages. Programming languages here. Okay, this one. All right, looks like 90% of you have voted. So let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay. So right now, why don't you guys go into the group discussion and chat and share your thoughts about the answer within your group. And then after you guys are done, come back. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so after discussion, okay, so let's see. Okay, so before, well, this is what you guys have after discussion. So most of you think Python and has consume the most will generate the highest instruction count. And before discussion, this is what you guys thought. Before discussion, Python slightly higher and Java also not is the second highest. So I'm inviting one of the group to share, and it looks like Hayat, you already have the whale want to share. So why don't you just shout it out?
Yeah. So I did Python, and I think most of us did either Python or Java as well, because we thought that C and C++ are like they're closer to assembly language than the other languages are, and they're less high level than the other languages. Python is a very high level language, very far from assembly, and that's why it would have a higher instruction count, printing hello world on screen.
Okay, so how about Java and versus Python?
Yeah, Java as well. We were not sure which one would be higher, so but we went for Python instead.
You went for Python. Okay.
Yeah.
Any other thoughts? Okay, I have raised the hand. Kevin.
Hey, can you hear me?
Yes.
Okay, cool. Yeah, sorry, my PC blipped out during the breakout room, so I didn't really discuss it, but I put Python down because it's an interpreted language. It has to go through an interpreter, and it just seems like there's so much overhead in that at runtime.
Okay, Elliot.
I was going to make a similar point about Python being interpreted, although Perl is as well. I had to look that up. I didn't know that before, but at least on the other side of that, the compiled languages have like the advantage of during compilation you get to do optimizations that might result in fewer instructions.
Okay, so looks like everybody is cool for the answer should be Python, right? And sometimes for this kind of question, just running it directly would probably give us the best evidence. So, well, as a computer science professor, I really like to write code, and it's like writing code is actually one of my favorite hobby every day. So, and Hello World is such a simple program that everyone should know how to write, right? So now I am showing you different versions of Hello World with several different languages. So the first one that I want to show is the C programming language. We have 1, 2, 3. Well, we have 6 lines of code, or say, something like this, right? 6 lines of code, and GCC. Well, I don't even want. Well, okay, let me optimize it. Although I'm pretty sure that optimization won't make any difference. So now, remember our group friend perf, right? It will generate the instruction count and all the information that we need to judge if the program is performing efficiently or not. So let me run this, right? So for C programming language, come on, can you believe that 6 lines of code takes 652K instructions to execute Hello World, right? Such a high overhead instruction. Don't you believe? Can you believe that, right? And now, let's look at the C++, right? So C++. Well, also about the same number of lines is, although for C++, because of the object-oriented, include the standard library, you use the C out instead, right? Doesn't looks too different from the C version. And so let's see how many instruction it takes for the CPP version, and I just compile it on the fly. Oh, shoot. Okay. CPP. Wait a moment. Do you remember what was the last number? 650K. And we already saw it's a lot, right? But with C++, it's 3.2 million. 3.2 million, right? That's a lot. Let me try to optimize the code a little bit to see if that changes things. Still, 3.2 million. Did you see that? 3.2 million, right? It's a lot. All right. And now look at another language called Java. And I can definitely use, well, here is the hello world dot Java. Okay, public class, hello world, main, system out, that print line, Java, that's Java. Java C, hello world, that Java. Okay, it generates that, right? And if you remember how to run Java, you have to invoke Java by a virtual machine. So Java hello.class. Or just hello world. Did you see that? Also, oh, wait a moment. Could not. Oh, here we go. We have hello world printed. And for this particular hello world, it takes 145 million. 145 million. Okay. So now look at Perl. So, you know, when I was a child, during my childhood, people say that Perl was the most beautiful programming language. So if you are a big fan of programming language, Perl is definitely one of the programming language that you should explore. So let me try to run Perl. Hello.pl. Okay, so for Perl, it takes 16 million instructions. 16 million instructions. All right, now finally, our favorite Python. Python hello.py. Okay, yeah, let me check. Let me check. Okay, so just one line of code, hello world, right? Python hello.py. Oh, right, it takes 38 million instructions, right? So for this 5 that we just mentioned in particular, it seems like Java would consume the most, and then Python, right? So in terms of a performance, Java is definitely the worst, right? So if you want to go back and track, right? So for the C programming language, it only takes 650K instructions, 0.006 seconds, right? And for a CPP, it takes 3.2 million, which is almost 5 times more instructions than the C, and it takes 0.004 seconds. And for even with compiler optimization, it doesn't change the instruction count too much. And for the Java, it took 205 million instructions to just implement, here, 145 million instructions to just print out the hello world on the screen, and it takes 0.08 seconds. And for the Perl version, it takes better 16 million instructions and 0.05 seconds. And for Python, it's 39 million instructions, 0.02. So ironically, right, the two programming languages that you guys favorite the most are in fact the slowest. Well, sorry, one of the programming language that you guys favorite the most is actually one of the least efficient programming language, right? So that's interesting, right? So some of you were saying about, Professor, you are kind of out of date. So we have some new programming languages right now. So For example, we have the Go compiler. So we can do like Go run like hello world.go. Right? It also prints hello world. Okay, let me modify this a little bit. Okay, so this is to make sure that, okay, it prints exactly the same thing as you guys want, right? So this is Go. And if I do sudo perf set go run, see, for Go, it takes even worse, right? Didn't you see that, right? It's not, it's one, well, it's, what's the next? It's not million, right? It's trillion, right? 1 trillion instructions to just print out hello world, right? It's even less efficient than Java. And well, so some of you would definitely say, okay, Go actually can also be compiled, right? So let's do hello world, go build hello world.go, right? And now let's run the hello world generated. Okay, with that, it's more efficient, 1.9 million, but still not as efficient as C programming language, right? And some of you think about Rust. People say Rust is really fancy, it's very efficient. So let's see how efficient is Rust. So this is Rust. And if you want to okay, so let's make it the same output. So let's do Rust. Rust C hello world.rs. Well, compile takes a lot of time. Takes a lot of time. Okay, finish compilation. Let's run it. Rust. Okay. Okay, it takes 1.6 million, but still not as efficient as C programming language, right? So don't you feel that, right? That your favorite programming language might not be the most efficient, and even new programming language is probably not going to be more efficient than the programming language that you think is a grandfather old one. So that's why in performance programming, when we choose programming languages, and you can see that for some programming language, when you are talking about performance programming, it has its own disadvantage that others can never compensate for that. Like if you are having a programming language that its overhead is so high, how can you make it efficient, right? So sometimes it's really important that you can choose the right programming language if you do care about performance. And the fundamentals of making the difference, I don't think I have to explain this too much, right? But for C, it's a one-time cost. So you don't have to recompile your code, and the code is very efficient. And sometimes people were asking about then why C++ is so inefficient, and thinking about what's the difference between C and C++ is that C++ has a concept of object-oriented programming. So you can imagine all the additional overhead are coming from there. So every time, even though I'm doing output, I have to create an object first, and nothing is zero cost. So when you create an object, it also consumes instructions. So that's why C++ always have such a high overhead compared against Rust or Go that doesn't have the concept, doesn't necessarily need the concept of object-oriented programming. So for Java, it's the worst in terms of instruction count, and in general, the worst in terms of performance. And the reason is because even though it has a compilation process, but the compilation only get it to Java bytecode. And the purpose of Java is that they want to make Java program portable to all platforms. So it makes no assumption regarding how many registers a machine can have. So it turns out what's really bad is that for Java, its bytecode, it's based on an architecture called stack machine, which most of the operation will be later translated into memory operations, which every time you need to calculate the effective memory address, you cannot use registers efficiently. You have to frequently move things around. And the translation itself, a dynamic translation between the bytecode and instruction happens every time. And because of the machine architecture that it makes no assumption on the underlying architecture, it's hard to have the bytecode aligned with the underlying architecture. So turns out that's why Java becomes the least efficient, even worse than the translator, because thinking about the interpreter is similar to the Java virtual machine in a way that it's translating instructions from a higher level code to a lower level code. However, for Perl or Python, because the interpreter can be spatialized both in can be spatialized for the underlying architecture, so it could potentially generate fewer amount of instructions as Java, and the translation itself could also be made more efficient. So that's why even Perl or Python is interpreted-based language is still better than Java. So one thing that you should probably learn is that, okay, if you are talking about developing a large-scale project that's really aiming at performance, then you should probably thinking about choose the most efficient programming language that you could have. All right. So now the next question that I want to ask is that how compilers affect performance in your from what you think. I mean, affect performance. Okay. All right, let's wrap up in 15 seconds. Five, four, three, two, one. Time is up. Okay, in the meantime, I'm inviting one of the group to share your thoughts with us. Okay, David.
I guess so. First, we all agreed that it affects the CPI because because it's like because the compiler determines like how the memories are accessed in like on like an instruction level, right? So like like from the example previously shown, just like the way you manage certain memory can affect the CPI, and then so that's the performance on that aspect. And then also, but we're not we didn't really agree on instruction count, but I think the compiler also affects the instruction count because you can like like for example you can have a more optimized compiler that translates into less instruction code than like a less optimized compiler, and that's like entirely dependent on like the compiler, like how the compiler is implemented, right?
Okay, so David, you are in group red. So congratulations, group red, you score 1. So probably the easiest thing to do is just show you a demo regarding what's the effectiveness of compiler. So do you remember the matrix addition example that I just demoed? And now I have 2 different versions of them. One is adding the -03. So we can see, and which means that, and the original one is -00, which means that we don't do any compilation. Compiler optimization. And again, I'm using our good friend Perf to see what's the difference between different versions of code. So this is the original version of matrix addition, which is not optimized. And okay, I think it takes too long. So let me just do this. Maybe this is probably good. And let's see like how many instructions it takes to execute this pieces of code. And okay, so right now, if I run this, right, you can see it takes, wow, this is million, this is million, this is trillion, 65 trillion instructions. And the IPC, or say the CPI, is 0.24, right? Given it's 1 divided by 4. So now, if I am running this optimized version, right, we can see it should, wow, it takes a lot shorter time, right? So originally it's 3.2, and now it's only 2.6. And in terms of instructions, originally it takes 65 trillion, but now it's only 44 trillion, right? So it does reduce the instruction count. And because when you reduce the instruction count, you also change the percentage of the type of instructions. So turns out the IPC or CPI is also different. So that's so as you can see, right? Compiler can change both the instruction count and the CPI. And another interesting thing is that if the compiler is smart enough, right? And if you do remember the last demo, there is a significant difference between the performance of the version A and B. But now, if I'm also optimizing the version B, does that change the execution time? The answer is not really, right? So what does that mean is that although the compiler can do a certain amount of optimization, but there are still some basic things that the compiler cannot heal you. So for example, one very high-level guideline that compiler optimization is limited is that the compiler should not significantly change the behavior of your program in a way that not make your program wrong, right? So they can only change your instruction count, change your CPI with very limited scope. So if you don't have a peace of mind, like how can I write efficient code, even the compiler optimization cannot help you. So in the past, I would dig into more detail about the compiler optimization, but with CSE142, your second lab would navigate you through a rich set of compiler optimization, so which we will talk about in the lab 2 today. So if you're taking CSE142L this summer together with me, you will hear more about what the compiler optimizations can do for you, or compiler optimization cannot do for you through the lecture, a lab lecture tomorrow, or going through the lab tomorrow. So I will leave most of the compiler experiments for your own interest, and you will learn that through the lab anyway. So, but one thing that you have to remember is that compiler can indeed reduce the instruction count, change the CPI, but very limited. Like the demo that I just showed you, right? It cannot really change the version A from the version B from the version A. And so if you write your cronny software, there's nothing the compiler can help you. So as a summary of the CPU performance equation, performance equal to 1 over your execution time, and it's composed of instruction count, CPI, and cycle time. And programmer can affect all the factors. The instruction count, the programming language, the compiler can only affect the instruction count and the CPI. And for the cycle time, it's mostly the process technology or the microarchitecture effects. However, programmer can also control what cycle time I want to use. So now, one thing, right? We want to talk about, one of the topics that I mentioned today is that we want to get better. But how do I know by how much am I doing better? So we need a definition. So now I want to test you if you know what the right definition of speed up in computer architecture. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, it looks like we definitely need some kind of group discussion. So open the file that I sent out through the chat and go into the breakout room. All right, let's wrap up in 15 seconds. Five, four, three, two, one. Time is up. Okay, so well, three of you raise your hand, but looks like David, you got the earliest. So why don't you share? And David, you are in Team Red. Okay.
Yes. So our group, we said answer is 4D, 1.25.
Okay, how did you derive that?
So I think the simplest way, because you want to know how much y is faster than x. So you want to know the execution time of x divided by the execution time of y, right? So since it's a ratio,
so slow down, right? So you said you want to know the execution time of y divided by x.
X divided by y.
Okay, so right. So here's the thing, right? Well, stay unmuted. I'm just explaining things, right? So if you read the book, right, the only definition in computer architecture in terms of a speed up is if we want to say y is n times faster than x, it must be the execution time of x divided by execution time of y. Okay, keep going.
Yes. So since it's a ratio, right? And then we know that they have the same was the middle column. So we can ignore that. And then we just need to care about the clock rate and then the CPI. So yeah. So the first one we have 3 CPI divided by the clock rate. So 3 divided by 3 is 1. And then the second one is 4 divided by 5. So yeah, 5. Yeah, 4 seconds.
So that's how you guys get 1.25, right?
Yeah.
All right. Hayat, do you have objections on his question? On his answer?
Yeah, the same answer.
Okay.
Can
Awesome.
I add something real quick?
Okay. Yeah. So after discussion, right, I think we all agree, and it's also consistent to your voting result that every of us agree that, well, speed up is equal to, if we say y is n times faster than n, or the speed up of y over x is the execution time of x over execution time y. There's no other definition, right? So the answer for this question would be D. And this is how we calculate it. Oh, right. So that's the simple definition of speed up. So now we are on the same page. This is speed up. And now I'm going to talk about, so we have been learning the Moore's law. We have learning the CPU performance equation. And this is the third equation or third law you have to memorize in computer architecture. And this is called M-DOS law. So this is the format of M-DOS law. Wait a minute, it's also talking about speed up. So the speed up of the enhanced system is calculated as 1 over 1 minus f plus f over s. And the f is the fraction of time in the original program that where you are going to apply the optimization to. And the S is the speed up that you can achieve on the execution time you spend on F. So that's the definition of M-DOS law. And wait a minute, right? Professor, what you just said, there's only one definition of speed up. Shouldn't that be just execution time baseline over execution time enhanced? Why do you show me this? So M-DOS law is nothing but a different expression of the speed up that I just introduced. So you can imagine the whole idea of M-DOS law is that I scale the total execution time back to 1. So you can imagine your program, and if and f is the portion of the execution time that you can apply a certain optimize on. So your total execution time can be divided by 2 parts now in a baseline program, which is f and 1 minus f. And if you can enhance f, so when you enhance the program, right, if you can enhance f, 1 minus f remain the same. But for the f part, which is the red part here, could be speed up by s. So it only takes f divided by s amount of time. So if you think about the baseline is 1, the enhanced part is indeed f over s plus 1 minus f, and that would give you the m-DOS law. So that's where m-DOS law is coming from. So now, as a practice of m-DOS law, I want you to try this problem set that I create. That's based on some of the real life experience. As a gamer, some of you probably know this is what this is one of the popular online game, right? The Final Fantasy. So now people were complaining on Reddit, well, Steam, saying that, oh, not Reddit, Steam, saying that, well, Final Fantasy 15 spent a lot of time loading a map, within which we further profile that 95% of the time is spending on accessing the hard disk drive, and the rest in the operating system, file system, and the IO protocol. So seems like hard disk drive is the most critical part. So we replace the hard disk drive with a flash drive, which or say a solid state drive, which provides 100 times faster access time. So now, by how much can we speed up the map loading process? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so looks like after the first round, I do feel that we really need discussion. So go. All right, looks like everyone is back. And if I give you 5 seconds to get your votes in. 5, 4, 3, 2, 1. And looks like Elliot, you guys got it. So why don't you share your thoughts with us?
All right. So you start with the fact that like the hard drive is only being accessed 95% of the time, right? So there's 5% of the time that you can't really affect it by changing out the drive. So we set that like 5% aside. And then so we're working with this remaining 95, which is being sped up 100 times. So you can divide that by 100 to get 0.95. You can add that back to the 5 to get 5.95. And so now we have this.
So it's 0.005 and plus.
Oh yeah, yeah. Sorry, I was doing it with 100 on the top, and that was a little bit easier for me in my head. Sorry, but like yeah, it's with 1 on top, it would be like this. Yeah.
Okay.
Or something like this. Yeah.
Okay, then the answer would be C, right? Because if you if you put that in the formula, right, the answer would be C. And so that's why this discussion is really helpful, right? So in the second round, this is what you guys think, right? And this is what you guys think in the first round. And do like, okay, right? The first round is like, okay, what the heck is going on? So that's the value of discussion, right? So, and thanks Elliot and Group Yellow for sharing your thoughts. And right, so and also, right, it's actually an easy way for you to easily estimate, okay, if this is the rough amount of the speed up and I can get, and this is the benefit that I could expect, right? So, and in fact, you can apply MDOS law in multiple optimizations. So, for example, right, if I have disjoint optimizations saying that like optimization 1 and optimization 2, and they both get different speed up, then you can extend the speed up formula like this: 1 over 1 minus FOPT1 minus FOPT2, which is essentially this graphical representation, and then plus the speed up of each portion. And if they are not disjoint, then it takes you a little bit more effort to figure out what both could be affected and what each individual part. But even though you want to apply MDOS law on multiple optimization in your program, just remember, right, it's just a reformat of the speed up equation. So as long as you can divide the baseline execution time into several different disjoint parts and apply the speed up on each of the speed up on each of different disjoint part, then you should be able to get the estimated speed up as well, right? So that's MDOS law. So now the second run of the MDOS law question is that I want you to figure out that, well, I think I'm missing one of the slide here. Okay, so anyway, all right. The second run of the MDOS law, actually, let me see. Is this the color, right? Okay. Sorry about that. Okay, so the second run of the MDOS law is that, okay, so if I have, I want you to practice one more time for this question. So why don't we go ahead and, okay, sorry. Jump to the wrong one, right? So now what I'm saying is that, okay, so this is the practice that I want you to do for multiple optimization in a way that, okay, what is this question about? If we replace the hard disk drive with a flash and also a better processor to accelerate the software by 2 times, right? Which is the multiple parts speed up that, as I mentioned, right? Then you can apply the extended MDOS law in this way: 95%, 5%, and 100 times speed up and 2, and put it together. That will give you around 29 times speed up for the MDOS law if you want to apply it on multiple parts. And now I do have a question for you. Okay, so with the latest flash memory technology, the system spent 16% of time on accessing the flash. and the software overhead is now 84%. If you want to adopt a new technology, then that makes the flash faster to achieve 2 times speed up. How much faster the new technology needs to be? Can you try that? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, looks like for this question, we do need group discussion. So why don't we go ahead and have the group discussion real quick? All right, let's wrap up in 15 seconds. Send your vote in 5, 4, 3, 2, 1. Time is up. Okay, Michael, you got it. Shut it out.
Our group put E, none of the above, and I think it's because like the whole essence of Amdahl's law is that you can't be faster than the slowest portion, and in order to get 2 times speed up, we'd need 1 divided by 0.5, right? But our slowest portion is 0.84, so it's just impossible.
Right, so it's impossible to achieve that speed up, right? So if today, well, you know Amdahl's law, if your boss in Square Enix is asking you to accelerate the process of speed map loading by exploring new memory technology, you know that your boss is basically asking you to leave because you are he is giving you or she is giving you mission impossible, right? So that's another thing that you should learn about Amdahl's law in your real life that help you to estimate where is the limitation. So we will continue our discussion on Amdahl's law tomorrow, but don't forget we also have a reading quiz due tomorrow before the lecture, and we will drop the lowest of your 2 list performing reading quizzes, and you have 2 shots, unlimited time. We take the average. Discussion session today starting at 5 p.m. led by the TA. He will share his opinion regarding what's the most efficient way to get your assignment done, which due Sunday midnight. And check our website for slides, Canvas for quizzes, Growscope for assignment submissions, and Piazza for discussions. And if you missed any of the lecture, please visit our YouTube channel. Other than that, enjoy the rest of the day. I will meet you tomorrow.
Professor,
Yes.
where can we find the discussion recording or discussion?
I will share with you later on Piazza if I have the recording. Okay.
Okay.
Thank
so
you.
much.
Thank you, Professor.
Goodbye.
Is the
Professor.
Yes.
is the discussion Zoom link going to be the same as the lecture link here?
Yeah, it's the same
Okay.
with the lecture link.
Thank you.
Is it 5 or 4?
Question?
Yeah, Professor, can I ask a question?
For
Just
what?
I would like to show you my data hub really quick because I don't know what's happening.
Well, if you are having question regarding the lab, you should go to the lab office hour, not the lecture now. And
No.
we
The
have
thing is,
we have.
I can't access my data hub.
Mhm.
Right now, it was written welcome to CSE 142 L,
Again,
but
this is okay.
when I go inside it, I can't see anything.
Well, so for this, you have to ask help in the lab session, the office hour session. I cannot help you right now.
What if they're not they weren't able to fix it by Friday?
Well, I don't think we will figure that out, but this is not something that I can help you on the spot right now.
No, I mean, at least if they weren't able to fix it by tomorrow, at most.
Well, I mean, if you can access Data Hub, then I don't think there is any other issue.
Yeah, the thing is that I can't access it. If they're not able to fix it by tomorrow, at least can I get
No, I
extended?
don't. As long as you see that, there shouldn't be any issue with the lab. If you need further assistance, try to find a tutor during the tutor session. Is that okay?
Okay.
Okay. Samuel.
Hi, I wanted to ask whether discussion was at 4 or 5 because
It's at the same time as I think it's 5.
Oh, okay, WebReg says 4, so I was just wondering.
Oh, WebRec says 4.
Yeah.
Okay, then it's probably 4. Sorry about that.
Okay, thank you.
Goodbye.